And thank you organizers to giving me this opportunity to present this work in the international forum. So today I'm going to talk about the collaborative work, which is done with Dr. Surjit Paul, my PhD supervisor, and close collaborator, Matthias Wolf from TLS, Germany. So this work is based on the particle acceleration. So basically, the electrons accelerated from the thermal pools to suprathermal or very high energy at the cluster shock fronts. Okay, so before going to the methodology or jump to the methodology, I will give a brief description about or say why we are actually interested in this task. Okay. Okay, since for long, many galaxy clusters are being observed in radio band, typically in 150 megahertz to 2.5 gigahertz, and many different radio structures are being observed. So, as earlier talks already told about the radio halo and radio relic-like structures. So, radio halos are the diffuse emission or at the cluster center, which is strongly coincide with the X-ray emission in the medium. Whereas radio relics are the radio structures which are found very near to the periphery of or near to the virial radius of the galaxy clusters. Okay, so I'm not going into the description of radio halos. My main focus is in the radio relic part. So what would be the possible reason for getting these radio relics? One possibility from the simulations, we observed that these structures has a strong resemblance with the cluster merger shocks. Okay, so the possibility for getting the high energy charged particles in that medium at the cluster outskirt is due to some particle acceleration process around the shock. Okay, and so the radio emission which I am going to talk about is due to the synchrotron radio process only. Okay, so this is just radio emission of power from a single electron where a magnetic field is required, and this F function is the synchrotron function having this morphology which peaks at 0.29 times of the critical frequency. Okay, but this corresponds to a single electron only. But ideally, in the system, we have some distribution of electrons. So, for getting the radio emission from that distribution, we take this equation. Okay, so this takes us about the distribution of the electrons either in the momentum space or in the electron space or in energy space. Okay, but here I am taking the momentum space. Okay, yes. So one more thing, the synchrotron radio emission means detecting synchrotron radio emission from galaxy cluster medium or the ICM is actually the direct evidence of having the high energy charged particles and the magnetic field, in the presence of magnetic field in that medium. Okay. Yeah. So here I discuss or I considered the diffusive shock acceleration as the strongest particle acceleration process, under which the relativistic electrons taking the form of inverse power law. Okay, like this, where this spectral index is strongly correlated with the cluster or the medium properties, hydrodynamic properties. This R is actually the compression ratio. Okay, which is the ratio between the downstream density and the upstream density. So D stands for the downstream and mu stands for the upstream. Okay, so which can be further correlated with the Mach number and the gas constant used or adopt in the medium. Okay, but since we want to simulate or we want to numerically model this process, we need some exact form of the distribution, electron energy distribution. For that, proportionality constant is taken care by this normalization one. Okay, and we set some cutoff in the momentum also. But now the point is how to compute this normalization constant. Okay, so one possibility or the simplest possibility is that compute the total kinetic energy present in the relativistic electrons within some range, let's say P minimum to some P maximum, and equate it with the energy deposited by the shock to the thermal electrons to get accelerate to high energies. Okay. So with this, we actually equate the total kinetic, the relativistic kinetic energy with the energy or some fraction of energy injected by the shock front. So there are actually two possibilities for calculating the energy or the shock energy. Means how much amount of energy is actually can deposited by the shock in the downstream. Okay. So first one is just computing the downstream energy, means that energy gained by the gas in the downstream, considering the adiabatic process. Okay, so with this one can compute the shock energy. So this Q is actually the entropy ratio, entropy in the downstream divided by the entropy in the upstream. Okay. It is again closely correlated with the compression ratio and the gas density, but it's a very complex relation. And one more possibility to compute this shock injection energy is by getting the kinetic energy flux, okay, at the upstream and at the downstream. So it will give you the what amount of kinetic energy flux is available at the shock front for the acceleration as well as for heating effect. Okay. So yes, that epsilon naught is sorry, xi E is actually this will taking care that how much energy is actually dissipated into the non-thermal part, or means to accelerate the thermal electrons to suprathermal or the relativistic case. Okay. So with this, we took the following assumption. That means for this modeling, considering the thermal electrons only, means the electrons are actually accelerated directly from the thermal pool. No fossil electrons are considered during this modeling. And the second one, the thermal pool electrons follows the distribution of Maxwellian-Züttner distribution. And why so? Because this is just a relativistic correction to the Maxwellian distribution. And since our system are actually at the temperature 10⁷ to 10⁸, so the particles or electrons have some momentum in the relativistic region also. So we want that corrections. Okay. And yes. So that fixed amount of energy which goes from shock to the non-thermal part is about 5% that we assume. Okay. And next is the diffusive shock energy spectra is which we assume that the diffusive shock spectra is the extension to the Maxwellian distribution. So by this I mean that so suppose you have thermal distribution. Okay. So some amount of energy electrons from this thermal pool will goes to the DSA spectra. Okay, and this intersection actually gives you this P minimum, which stands for what is the minimum momentum that is required for the thermal electrons to get accelerate to high energies. So with this, we actually compute the relativistic electrons or the fraction of relativistic electrons that can goes to the relativistic region, following both two methods. One, the change in thermal energy, and another one from the kinetic energy flux. So we got that okay. So this is the fraction of relativistic electrons. And in the x-axis, we plot the Mach number. Okay, so in both the process, yes, one more thing. Here I considered the density a constant. Okay, for all the Mach numbers. Okay, so for the constant density, as we go further in the Mach number, the number of relativistic electrons or the fraction of relativistic electrons actually goes down, and that trend is followed in both the energy injection process. But only one difference is there for the Mach number below 3. If we consider the thermal energy change as the energy input, the fraction is around 1% only, not 1%, 10 to the power minus 2% only. Whereas for the kinetic energy flux transfer, this fraction goes to 10 to the power minus 1%. Okay, so we usually think that if you are getting high number of electrons in the low Mach number, so there is a possibility that you may receive high radio synchrotron emission as well. Okay, this is just for the comparison part. So in the lower region, for Mach number below 3, you have about 10 times difference in the process for getting relativistic electrons. But if we compute the radio emission corresponds to these processes, both the processes leads to the same radio emission. Okay, and one more thing for the radio emission. So this radio emission is actually computed for each shock cell. So those shock cells are actually taken from our simulation of 10 to the power 15 solar mass galaxy cluster. Okay, and within the radius of 2000 R2000. Okay, means where the over density is equivalent to 2000. Yes. So what we observe from this plot for means the shock with strength less than 2.5 Mach number are very less efficient to give rise or ignite the radio relics. Okay, so some additional electrons or acceleration process or some other stochastic process is actually required if means low Mach number shocks accelerate the charged particles or gives rise to the radio emission. Whereas the high shocks are actually giving the high radio emission, which is in the detectable range. So, thank you.
Yes. Thank you for the nice talk. I found that there is a important factor in your work is P-mean.
Yes.
Can you tell something about its significance first? And secondly, what is the range of its values?
Okay, so actually a P-min for our case means considering temperature 10 to the power 7 to 10 to the power 8 is around, so means I'm not telling in terms of gram per centimeter, this thing. Okay, so it relates with gamma, and that gamma corresponds to 1.02 to 1.08 for this particular, 1.02 to 1.12. Yeah. And if you want to see the significance is actually hidden in the integral part. Yeah, in this way. So when you are actually integrating or computing this kinetic energy, okay, so there is some integral part which is strongly dependent on this gamma factor. Okay, and that gamma factor gives you that if P minimum is less than 5, okay, so for gamma less than 5, low Mach number shocks are less efficient to accelerate the charged particles. Okay, so suppose if you increase this P minimum, let's say to 5, means gamma to 5, then there is the possibility that the low Mach number shocks can accelerate the charged particles to very high energies or more efficiently. Okay, and that's why it is claimed that for the low Mach number, you need some fossil electrons also to emit in radio.
Any
How
other
do you
question?
compare these two these calculations with massive clusters and the ones which he showed this morning, which are less massive? Is there going to be any difference or?
No, according to this radio emission, there would not be difference because density and temperature or the Mach number is almost same. According to the distribution. But when we applied it to the direct simulation to create the mock radio maps, so we saw that there are higher possibility to get radio emission from the galaxy groups. So low mass galaxy groups.
Yes, one question.
Observationally, can we find evidence of shocks
Yes, yes,
through X-rays?
yes. Through X-rays.
Apart from X-rays, are there any other?
Apart from X-rays.
I do not know. So just ask.
I may not be aware, but I think that only
It
X-ray.
is possible via radio, right? When the shock regions are the ones which are highly polarized.
Well, radio is fine. X-ray is also there, but optical IR from line ratios.
That's where you expect to have a lot of star formation activity going.
And also these.
Metallicity. I mean, if it is internal, then you can. Magnetic field compression is there, so metallicity is very different.
So this radio and X-ray morphological association.
Yes.
Yes.
Not only morphological. I mean, in position.
Radio and X-ray.
Yeah.
Any other question? Anything from the online? Okay.
No, there's.
Okay. Then let's thank Prateek and.
Long live India and France friendship.